we have seen so far that if we have a linear map, we can always express it in terms of a matrix, where this matrix always corresponds to a fixed choice of basis vectors in our source space and in the target space. There are many situations in linear algebra where maybe we start with one basis, but in the end it turns out to be much more convenient to work in a different basis. Maybe it's a basis in which the linear mapping looks much nicer. And then sometimes what we want to do is, even though we know how the matrix of the mapping looks like in a particular basis, we need to change the basis. And then we want to know how the matrix changes if we change the basis. And this is what I now want to show to you how this works. And to start off, we consider the simplest of all mappings that we could conceive, namely the identity mapping. So consider the identity mapping I from V to V, X maps to X. Standard identity mapping. Now, how does this mapping, this happens, the identity is also a linear mapping, so we can express it in a basis. Assume we fix a basis, a basis of V. No matter what the basis is, this linear mapping is, if we choose the same basis on both, like in source and target, then this linear mapping is just the identity matrix. So assume we fix a basis of V, and I stress both in source and target space. So we use the same basis on both sides. Then the corresponding mapping, the corresponding matrix looks as follows. And maybe I make it explicit. So the matrix of the identity mapping, if we have a basis in the source space and the same basis in the target space, it is just the identity matrix. This is an identity matrix depending on the dimension of the space, and like once on the diagonal and zeros everywhere else. And you might want to consider for a minute why this is really true. Why is the identity mapping represented by this matrix? But it's easy. And now we want to consider the situation where we don't have the same basis in source and target space. So now consider a basis A, which I call A1 to AN, and B, which is B1 to Bn. Both are bases of, consider A and B both bases on V. And now how does the identity mapping look like? So the question is, how does now how does the matrix of the identity mapping, and I make it explicitly, identity from V with the basis A to V with the basis B look like? This is the question that we want to answer in the first place. Okay? Now this could also be an exercise on one of your assignment sheets, because we have already seen how to construct the matrix of a mapping given that we know all the bases and what does the mapping do. So how is the procedure to find this out? You need to find out how the basis vectors of the first space are being, in this case of the first basis, are being expressed in the second basis. Maybe I write it because A and B are, maybe I write it differently. Because B is a basis, because B is a basis, we can write each vector of the original, like if we now consider a vector that is in the original basis, one of the A vectors, we can express it in terms of the vectors B. We can write each of the vectors in A as linear combinations. So what we get is we have, for example, the vector A1 is T11 B1 plus T12 B2. Sorry, I mixed up the indices, I think, in my notes here. This needs to be the other way around. T21 B2 and so on until Tn1 Bn. So say it again, we have the first basis vector A1, we can express it in terms of the second basis, B1 to Bn. So there exists coefficients T11, T21 and so on until Tn1 that express this vector. And I can do the same with A2 and I can do it up to Tn. So I can express all these vectors. And now we need to form the matrix. Now we form the matrix. The corresponding matrix T with these coefficients as entries. So we define the matrix T, which is T11, Tn1, sorry, I mixed up the indices. As I said in my notes, I think it's wrong. This is T1n and Tnn. And just to again color code it, this is sort of the green vector that we're looking at. And it ends up like, because this is the first basis vector, it ends up as the first column in our matrix. Let me just fix it in my notes, otherwise I forget it. And then this is n1. And this is 1n. And this is n1. Okay, close parentheses with black. Oh, no, sorry. Erase. Black. Okay, and this is now the matrix that describes the identity matrix. And maybe you might want to sit down and see why this is really the case. Why does this matrix exactly now represent the identity vector, the identity mapping of this basis transform? And maybe here is, let me sort of demonstrate it once more, why this is really the case. So the proposition is this matrix represents the identity. And to this, I mean, to check this, you simply need to check whether if you apply a vector to a matrix, you really get the correct result. So maybe start with a basis vector of A. So in the basis A, the first basis vector, A1, has the representation 1, 0, 0, 0, right? Because, I mean, maybe just as a side remark to really, what is the representation of a vector in a basis? We have A1 is 1 times A1 plus 0 times A2 plus 0 times A3 and so on, plus 0 times AN, right? And this is why if we express a vector, like a basis vector in its own basis, it is always one of these characteristic vectors 1, 0, 0, 0. And the position of the 1 indicates the index of the basis vector. Now let's consider the linear mapping. So if you now apply, and what we want to do is we want to now multiply this vector to t and want to see whether we get the correct vector back, right? So t times this vector 1, 0, 0. What is this? Look again at the matrix T, we just have it here. So this vector exactly gives you the first column. So this, if you multiply this vector to the matrix, you have to turn around the vector and take the sum row-wise. So what you get here is for the first row you get T1, 1. For the second row you get T2, 1, and so on, Tn, 1. So exactly, I mean, by definition of the matrix product, it has been designed the way that it works this way, you get the first column back, right? But now the first column is the one. Now this result is now expressed, supposed to be expressed in basis B. This vector gives us T of A, A1, expressed in basis B. At least if everything has worked out, expressed in basis B. Because this is the way it works, like it gives us the coefficients that we need in the basis of the target space. This means that the result is, maybe I write it down like this, T11 B1 plus and so on, Tn1 Bn. So this is the result of the mapping that is expressed in T, expressed now in the basis B. But by definition, this was how we had defined these coefficients of the matrix T. So check here. So here this green line says A1, the first basis vector, is T11 B1 and so on until Tn1 Bn. And this now is exactly A1. So what we get is that T of A1 is A1. Okay? So this is the formal way. I mean, of course, I've now just proved it for vector A1. This holds for all other vectors A in the basis A as well, and then it also holds for all linear combinations. So this matrix T really is the matrix that represents the basis, that does the basis transform for the identity map. And now the trick is that we can try to apply this to all kinds of more complicated mappings. Now there are a couple of propositions that I want to make. The first one is, what happens if we want to change the basis from A to B and from B to A? So we have two directions in which we can do that, how are the matrices related? That's the following propositions. So let A and B, I always don't get this B, A and B, be two bases of V. And now we consider the matrices of the identity mapping. Then the matrices M of the identity mapping starting with A resulting in basis B, and now the other identity mapping starting in basis B going in basis A. These two matrices are invertible, and each is the inverse of the other. And each is the inverse of each other. This is of course nice, it makes our life much easier. Now if you want to do a basis transform in one direction, we can write down the matrix. Now if you want to do the basis transform in the other direction, we just need to do the inverse of the matrix, and the inverse always exists. This is a nice property. I'm not going to prove it. If you want, you can try to prove it yourself. It's not difficult. And now comes the important definition, or the important proposition that tells us how to change the basis for a general linear mapping that we might have between different spaces. Let me first write down the proposition. Again, let A and B be two matrices, two bases of the space V, and consider the transformation matrix, A, which is the matrix of the identity from A to B, and A minus 1, the inverse, which is the matrix of the identity going from B to A. Now here I wouldn't have to define A minus 1, because the previous proposition just tells me it's the identity the other way around. And now I consider a linear map. Now let T from V to itself be a linear map. Linear. And now I consider two matrices, and X is supposed to be the matrix that represents T in basis A. So assume I have a fixed basis A, I express the linear mapping in this basis, and now I want to see what happens if I want to express it in this different basis. And X, the matrix, this is going to take too much place, sorry, I just write it in one line, otherwise we won't be able to see it on one slide. So we have X is the matrix of this linear operator T in the basis A. So this is the corresponding matrix. And now the statement comes, then the matrix Y, which is defined as A times X times A minus 1, represents represents T in basis B. That is, what I want to say is Y is the matrix of T in the basis B. Okay? And this proposition, this is really, really important. It tells us how we can do the transform of a basis. We start in one basis. Now we want to express a matrix in a different basis. And in order to do that, we need to construct this matrix A, which is the identity mapping represented in these two different bases. And then we apply it in the two different directions to the original matrix, and we get the new matrix. And this sounds utterly complicated to prove somehow, but maybe I want to give you a bit of an intuition, a figure, if you want to say, what that essentially tries to explain the situation. So let us start. We have a vector space jointly with basis A. I always write it in this way, so the curly letter always denotes the basis we have. And we have the vector space with basis B. And what we have is, we have the identity map. So, sorry, first of all, maybe I start with a different object. Again, here on the bottom, I also want to write V of A and V with basis B. And now let's start here. So this is the mapping we have. It is the mapping T. This is the linear mapping we start with. So the mapping is T. And the matrix that represents this mapping under these two bases, like A, curly A on both sides, the matrix is called X. And what I want is, this mapping, again, T, mapping T, and I want to have this matrix Y that represents the same mapping, but in a different basis. And now the question is how to do that. And the trick how this works is now, we need to go, so we want to start the mapping in the basis. So we want to start in basis B. This is our target. We want to have the mapping in the basis B. So we start with basis B. But now we need to transform this, first of all, the identity, to take it to the basis I. So this is the identity map. And the matrix that realizes this identity map is A minus 1 matrix, write it a bit nicer. Matrix A minus 1. And here, so what we do is we start with the basis B, we go with the identity to basis A, now we're here, then we go down with the linear mapping as we know it by matrix X to again the space with basis A, and now we need to go back, again the identity mapping, identity map, and the matrix is A. And if you now observe, this is exactly what happens in the theorem. Maybe I make a red box here. As I said, the composition of maps always has to be written from right to left. So at the right side we start with A minus 1. It takes us from the, maybe I just try to draw it once and then I remove it again. How can I do that now? Maybe in this way. So I start here. The mapping A minus 1 takes me to here. It is only the identity that changes the basis. Now I have this mapping T that brings me here. And finally I need to go back to the other basis that brings me here. This is the mapping A. And this is exactly what we have in this red box. From right to left we start with A minus 1, with X, with A.